Hey, welcome back. We're carrying on with Calc 1, in particular some new integral rules, in particular the natural log. Okay, so here we go. What is the rule? As soon as I get my pen working, I'll find that out. Well, before, of course, you know the derivative with respect to x of the natural log of x. And in particular, you could also play with the absolute value of the natural log of x. The derivative of that thing is 1 over x. So that implies that the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Okay, and we always need that absolute value symbol in there. Don't forget that. Okay. Then in more general terms, if we have some function of x, call it u, the integral will be the ln of the absolute value of u plus c. Okay, I don't know why we need to state that twice. No, these are just dummy variables. You can put any variable you want in there. And okay, so anyways, let's take a look. Here is an example. We have the integral of 1 all over 2x dx. And how do we do that? Well, we can factor out the 1/2. So this is the same as 1/2 the integral of 1 over x dx. And now it's in the appropriate form we want. So you're just going to end up with 1/2 times the ln of the absolute value of x plus c. Okay. Of course, you could do u sub if you wanted to do the thing in a different way. So there's usually more than one way to skin the cat. You'll find that in general is true. So anyways, u, we could just let be the denominator there. So du will be 2 dx. And then, of course, dx will be du over 2. Let's quarantine that. So I'll have the integral of 1 all over u times dx, which is du over 2. And then that'll equal, well, you can factor out 1/2. You have the integral of 1 over u du. And then use the formula. So that will be 1/2 ln absolute value of u plus c. And then, of course, back sub. 1/2 ln absolute value of 2x plus c. And then you may be, oh no, these answers are different. What did I do wrong? No, you didn't do anything wrong. You could rewrite this as 1/2 times ln of the absolute value of 2, which is just 2, okay, plus 1/2 times the ln of the absolute value of x, just using the product rule of natural logs, plus c. And then this thing is just a constant. So in the grand scheme of things, your antiderivative 1/2 ln of x plus c, this thing here represents just a family of curves. So there's this one in particular, which you kind of think, oh, there's the answer, but really that's just kind of a seed. That's just one particular curve in the family of curves. So, 1/2 ln, maybe it looks something like this, but it's a family of curves. So it's all of these characters, going up. And because of the absolute value, you can also draw the other side in like this. Okay. But that's just the exact same thing as this. It's just that this guy right here, this initial kind of position locator function, isn't the same as the other one. Okay. It's just shifted up. And so, yeah, it's that plus c that says, okay, this is a family, and the first guy before the plus c is kind of just, this is the shape, and then the plus c moves it up and down, and of course this is just like a constant of some sort. So you can take that constant and sort of combine it in with this c, and that will move it up and down. So you'd have 1/2 ln absolute value of x plus c resulting once you kind of combine this in with the c, right? So you're not thinking of, sort of the way I usually explain it is in terms of chess, right? So you have kind of a pawn, and a pawn can move pretty much anywhere, right? but if you put it right here, the pawn can move here, here, and here. So I don't know, but a king can do that as well, right? A king can move in those places. Maybe a better idea is a rook, right? Because a rook isn't going to be able to get everywhere on the chessboard. Hope you guys have played chess. Okay, so if a rook started here, a rook could move to this position, and then after it gets to that position, it can move to this position, and after it gets to that position, I guess it can move here. And then if it's there, it can move here. And then if it's there, it can move here. And then if it's there, it can move here. And then if it's there, it can move here. So it can move everywhere except in the middle. Okay. So this is just a starting place, is what I want to say. All right. The thing, big f of x plus c. This can just be any starting place in the picture. Right, so if a rook started here, it's going to end up filling the board in the same way. Okay, it can go here, it can go here, it can then go here, it can then go there, it can then go here, it can then go here, and then it can go there, and it populates the same. These are the same pictures. Okay, regardless of where you start your rook, you're going to end up with the same picture. Okay, so if you started maybe your rook right here, it could go 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 here, and then here. It's the same ending picture, regardless of where you start. So these integrals kind of represent the location of where you can end up on the chessboard, and it doesn't matter where you start on the chessboard, you're still going to have the same picture. Okay, so that's kind of the idea of this constant, and so if you do even get some other starting position, you can kind of factor that part out and then put it into the plus c part, and you'll still have the same picture at the end of the day. Okay, so I hope that kind of makes sense. It's a little confusing, that plus c thing, and I don't think it's really ever really explained, except that if you leave it off, we'll take off a point. But there is my sort of conception of the goings-ons. Okay, so let's get back to reality and take a look at some more examples. Okay, so I have 9 all over 5 minus 4x dx. And then, again, I'll let u equal 5 minus 4x. du is negative 4 dx. And I like to solve for my dx. That will be negative du over 4. Let's quarantine that. And so I have the integral of 9 all over u times dx, which is now negative du over 4. And you can factor out a negative 9/4, and we're left with our integral of the day, the 1 over u du, and we can integrate that negative 9/4 times the ln of the absolute value of u plus c, and then we can go ahead and back sub negative 9/4 ln absolute value of 5 minus 4x plus c. Okay, let's look at another one. So in this problem, they want you to find the area bounded by the region. So example, and more, that's kind of what we'll be headed towards, is finding areas of regions and things like that. X equals 4, y equals 0. It seems like you do a lot more of that in Calc 3, but instead of area, you're talking about volume and stuff like that. I don't know. Okay, so anyways, so what is this thing? You can plot it. So here's x equals 1. Here's x equals 4 about 1, 2, 3, 4. Y equals 0, of course, is the x-axis. And then this x squared plus 4 over x at 1, that'll be 5 over 1. 1, 2, 3, 4, 5. So right here. And then at 4, that'll be 20 all over 4, which is also apparently at 5. Okay. we could get the concavity and stuff like that if you wanted to figure out a nice picture, but it's just going to be something like this at the end of the day, and that's we're finding the area in there. Okay, so the integral will do that for us, an integral from 1 to 4 of this object, x squared plus 4 all over x dx. And then to integrate that, we're going to butterfly it. So just the reverse of finding a common denominator. You can take the two parts of the numerator and put them over the common denominator, x squared over x plus 4 over x dx. Simplify those expressions, so I have x plus 4 over x dx, and then each one of those we should be able to integrate, right? If you need to break it into two integrals, go ahead, plus the integral of 4 over x dx. The first integral is going to be x squared over 2, and we have to evaluate that, and then plus, I can factor out 4 from this guy, and end up with our integral of the day. So we'll end up with x squared over 2 plus 4 ln absolute value of x, and then we have to remember to evaluate from 1 to 4. Okay. So I'm going to end up with plugging in 4 first, 16 over 8, which is 16 over 2, sorry, which is 8, plus 4 ln of 4 minus 1/2 plus 4 ln of 1. ln of 1 is a 0, so I'm going to we'll find a common denominator here. 8 over 1, multiply top and bottom by 2, get 16 over 2 minus 1/2 plus 4 ln 4, which of course would just be 15 halves plus 4 ln 4. Okay. Let's look at another one. This one looks a bit nastier, but it's really just a natural log type problem. Did I put a number on that? Let's not put numbers on these because they're not the same anymore. Just call it an example. Okay, so 4x cubed plus 3 all over x to the 4th plus 3x. Okay, if you're in tune to a function and its derivative, you can kind of see that the numerator is just the derivative of the denominator. So you may be tempted to split it into two integrals, but that's really going to be a bad move. Okay, so here let u be the x to the 4th plus 3x, and then du, of course, will be 4x cubed plus 3 dx, which is basically the numerator there. Okay, so we could rewrite this as the integral of du all over u, which is our integral of the day. If you don't believe me, you could just rewrite that as 1 over u times du. Oh, yeah, that's obvious now. Okay, so that's going to be equal to the ln of the absolute value of u plus c, and then you're going to back sum. So ln absolute value x to the 4th plus 3x, and then plus c. Okay. And next, sometimes you got to do long division on these characters. So, example of doing long division. I have 2x squared plus 7x minus 3 all over x minus 2. So in general, that's a pretty good rule to have when you have a ratio of two polynomials where the high degree, the numerator has a higher degree than the denominator. Then you want to do polynomial division. Okay, so let's check that out. So x minus 3 divided by x minus 2. Okay, so what times x is 2x squared? Well, that'd just be 2x. So you get 2x squared minus 4x. Then you have to subtract these. Okay. So 2x squared minus 2x squared is 0. 7x plus 4x is going to give me 11x. Bring down the minus 3. Okay, so what times x is 11x? That would be 11. So you would have 11x minus 22. You subtract this junk. Okay, 11x minus 11x is 0. Negative 3 plus 22, 19. Okay, so I can now rewrite my, let's quarantine this business. I can rewrite my integrand, 2x plus 11 plus 19 all over x minus 2. Okay, so let's do that. This is the integral of 2x plus 11 plus, I think it was 19 all over x minus 2. Okay, that's all inside our integral. So the first two guys are just easy power rule type deals. So 2x squared over 2 is just going to be x squared for the first one. The second one will be 11x. The third one, you could do a u sub. It's not really necessary. So note, so we're doing an integral here. I'm going to let x minus 2 be u. So u is x minus 2. And then you see du is just dx. Okay, so there's no constant to float about. You'll just have 19 all over u. And then the dx, of course, is just du. So you don't really need a substitution. If you feel confident enough, by all means, you don't have to do it. Anyways, plus 19 ln absolute value of u plus c. And then, of course, back sub x squared plus 11x plus 19 ln the absolute value of x minus 2 plus c. Okay. Right. Let's look at another guy, another example. Just more and more examples. So this guy, x plus 1 squared dx. You may be tempted to FOIL that thing out. That's a bad move. What you want to do is just let u equal x plus 1. You won't necessarily be able to cancel out the numerator, but then you could rewrite the u formula to get an expression for x. So watch. So I'll get du is just plain dx here. So if I went into the integral and tried right now to replace everything, I'd have some trouble getting rid of that x in the numerator, right? So the denominator at u squared, the dx is just du, okay? But I can't proceed, I can't go through the gate if I got this x floating about. Right, so what do? Well, you just go back to the original formula for your substitution here and then solve it for x. So you get x equals u minus 1. And then you could go ahead and do your subs, right? So 2 times u minus 1 now all over u squared du. And then you could rewrite this as 2u minus 2 all over u squared du. And then you could butterfly that thing, and you get 2u all over u squared minus 2 all over u squared. Okay, simplify it. So I get 2 all over u minus 2u to the negative 2. Just prepping it to do a power rule on that second term. So the first integral will be 2 ln absolute value of u. The second integral minus 2u now to the negative 1 divided by negative 1. Should be just times negative 1. And then plus c, and then we need the back sub. So 2 ln absolute value of x plus 1 plus 2 all over x plus 1, and then plus c. One more example, and then we'll move on to trig functions. Here's an example. It looks a bit weird, but it works out. So 1 all over x ln of x cubed dx. So I'll let my u equal ln of x cubed. And then du will be 1 all over x cubed times the derivative of x cubed, which is 3x squared dx. Simplifying that expression, du will be 3 all over x dx, and then solve for dx. dx will be x all over 3 du. Quarantine. Okay. So we're going to end up with the integral of 1 all over x times u times dx, which is now x over 3 du. Okay, we need the x's to clear out, and we have that. No big deal there. We can factor out the 1/3, and then we're left with the integral of the day, 1 over u du. So this will end up being 1/3 ln absolute value of u plus c. And then you could back substitute, and you have this weird looking thing. 1/3 ln absolute value ln x cubed, and then plus c. Okay, it's a bit weird, but it happens. Okay. Okay, let's move on to trig functions now. The cool thing about this is we're going to be able to get the integral for all 6 of our, so I know sine of x dx is negative cosine x plus c. I know the integral of cosine x dx is just going to be sine x plus c, but the ones I don't know, right? What's the integral of tan x dx? Well, I don't know. What's the integral of secant x dx? Well, I don't know. What's the integral of cosecant x dx? Well, I don't know. And then what's the integral of cotan x dx? I don't know. Okay. Well, that mystery is going to be cleared up right now. I mean, we have some other integrals we could do, right? We have like the integral of secant x tan x. We know how to figure that out. That's just going to be secant x. But these other ones, the ones that you would think we should know, because we know all the derivatives, we don't know. Okay, but now we'll be able to figure them out. It's the long story short. So this next section, section 2, is on trig functions. It all come down to kind of doing some u subs based off of the quotient identities. So for example, tan x dx, well, tan can be rewritten as sine x over cosine x. And then you could do a u sub for cosine. So you just let u equal cosine x. And then du will be negative sine x dx. In other words, dx is negative du over sine x. Let's box that off and substitute. So the integral of sine x all over u times dx, which is now negative du over sine x. Okay. The sine x's will cancel. Goodbye. And then you end up with the negative integral of du over u, which will just be negative ln absolute value of u plus c. And then you could back sub. Okay, so you'll have negative ln of the absolute value of cosine x plus c. A word of warning, in the tables, if you've already looked this one up, you probably will see ln of secant, but this is equivalent. You're just doing a power rule. Okay, so if you take this negative 1 and treat it like negative 1 and put it into the exponent here, you'll have the ln of the absolute value of cosine x raised to the negative 1, right? Which is the same, plus c, okay, which is the same thing as the ln of 1 all over the absolute value of cosine x. And then that's plus c, of course. And then that's exactly the same thing as the ln of the absolute value of secant x, okay, plus c. So you'll see either one. I know them both because in my book they taught, when I took it 20 years ago, they taught it the first answer that I got, and now in the books they're putting ln of secant in there. So either one is fine. I know them both. Anyways, let's look at the secant then. So now we know the integral of tangent. I could kind of go back here and fill that in if I were so in. It's the either the negative ln of the absolute value of cosine x plus c, or it's the ln of the absolute value of secant x plus c. So these other ones we don't use as much. Okay, I'll just give you the secant version, which you probably won't have to have memorized either, but it does come up an awful lot. Anyways, how am I going to pull this off? This one is not intuitive at all. You can't really use a quotient rule because you won't get a nice cancellation. So what you end up having to do is multiplying, in this case, by secant x plus tan x, and top and bottom, dx. And then you'll end up having something you could do a u sub for. So you end up with secant squared x plus secant x tan x all over secant x plus tan x dx. And then you note if you do a u sub on secant x plus tan x, you just get the numerator. Du, the derivative of secant, of course, is secant x tan x. The derivative of tan is going to be secant squared x. dx. And of course that whole rigmarole is just the numerator. Okay, it's just sitting right there. So we can replace that. Let me box this off as usual. We could replace that junk with a du in the numerator and then just u in the denominator. And then that's the integral of the day. Ln of the absolute value of u plus c, back subbing ln absolute value of secant x plus tan x plus c. Okay. Okay. So you definitely need the tan one memorized. So memorize the integral of tan x dx is negative ln absolute value of cosine x. Of course, you can always derive that one just from what you know about natural logs. The other one, though, is a little harder. Dx is ln absolute value of secant x plus tan x. Okay. I'm not going to require you to know the other ones. I'm not even going to list them. But if you want, you can look them up in the book. Okay. It's just those two come up an awful lot, so we use those. The other ones look very, very similar. Okay. Okay. So, anyways, let's move on. So another example here: integral of cosine of t all over 1 plus sine t dt. And so I'll let u equal 1 plus sine t, and then du, that 1 will go away, and you're just left with cosine t dt. So again, that is basically just the numerator there, that cosine t plus t. So we can go and replace everything. That part in the top is du, part in the bottom is u, and we have the integral of the day, ln of the absolute value of u plus c, and then you can back sub ln of 1 plus sine t plus c. Okay. Let's do one. Do I have one more? Yeah, let's do one more where we actually have to evaluate. Doesn't seem like I'm doing much evaluation here, so let's at least do one of those. Integral from 1 to 2 of 1 minus cosine theta all over theta minus sine of theta d theta. So again, you can see the numerator is basically just the derivative of the denominator. So sine theta. So the differential is 1 minus cosine theta d theta. Okay. I'm going to drop the bounds and just put them in at the end. Drop the limits, excuse me. So I'll end up here with, in the numerator, du, and the denominator u. Let me box this stuff off. So I get the ln of the absolute value of u plus c again. Whoops, but we're not doing plus c. We have to evaluate. Okay, so I'm just remind myself I have to evaluate. Okay, back sub ln absolute value of theta minus sine of theta. And now I can put my limits back in, going from 1 to 2. So I end up with ln of the absolute value of 2 minus sine of 2 minus ln of 1 minus sine of 1. Okay. And you're going to need a calculator to figure those out. They're not like reference angles, like sine of 2. I don't know what the heck that is. Anyways, you put that in your calculator, you get about 1.93, and that'll do it. Okay, so it's just a lot of practice, and then every once in a while, maybe you'll have a weird substitution like this one. Okay, where you don't clear out all the x variables, and you have to do something creative. Now, in addition, now we will know how to do the integral of tan and the integral of secant. And you have to have these two new integrals memorized, and of course the ln integral, which is the integral of the day. Okay, so I think that's about it. Hopefully that chess thing makes some sense. Yeah, I think it does. And we'll see you next time. Thanks for watching, as usual.